Oh yeah, it can feel a little drizzle.
Yeah, lightning storm.
Lightning rod over here.
I'm just gonna crouch like this.
Yeah, it's the highest vision, right? Yeah. It's that
No,
weird.
there's a little metal thing on the top of that rock.
Oh, yeah.
Cut the legs off of our pants, threw our shoes into the ocean. Sit back and wait through the daylight. Sit back and wait through the daylight. Slip and slide on subway grades. These shoes are poor man's ice skates. Fall through like change in the daylight. Fall through like change in the daylight. I miss ya, the lines in my road. Some color on my Electron. Maybe I'll paint them in myself. Maybe I'll paint them in myself. Maybe I'll paint them in myself.
This is a strong acid. If you drink a strong acid, it'll kill you. And this is a strong base. If you drink a strong base, it'll kill you faster. Why will drinking acids and bases kill you? The body works off of chemical processes. If you drink a strong acid or a strong base, it will interfere with those processes and indirectly kill you. For instance, the blood has a pH, and I think it's around normally 7.4. If your blood pH goes below 6.8 or above 7.8, you die. Your cells stop functioning, and that would be really, really bad. Acids and bases are really important in organic chemistry because we use it to make other things. We'll take two high energy things, combine them in a way that we would like, and we get a low energy, but we get what we need. This is how they make pharmaceuticals and stuff. There are two ways you can look at acids and bases. Whichever way you use, pick the one that makes more sense to you and then use it for everything. So the Lewis definition is concerned with electrons. In the Lewis definition, an acid is anything that accepts electrons, and bases are anything that donates electrons. For Bronsted, it's the same thing, just flipped. For acids, they are anything that donates H+ ions. And for bases, they're anything that accepts H+ ions because they have the electrons to bond with it. Whatever you do, remember that acids and bases are opposite. If it's a strong acid, it's a weak base. If it's a weak base, it's a strong acid. Same with the conjugate acids and bases. Every time you look at a molecule, I want you to think, what role would this fulfill in reaction? Would this be an acid? Would this be a base? What does this do? So in this example, for methamine, what's the central atom here? First thing you should do. Well, it's going to be nitrogen because carbon's stable there. Hydrogens aren't going to do anything. From here, think, okay, this is a nitrogen. So what's its electronegativity? Well, based on it's like here, and then you go like all the way to fluorine. So based on this, nitrogen is not very electronegative. It also has a lone pair right here, since 3 bonds and Philosophes is octet and right a formal charge. So because of this, because it's the low electronegativity, it's not holding on very tightly, it wants to get rid of these electrons and react with something else. This will be a base. Another way to think of this is to look at acid and base having distinct jobs. A base's job is to get rid of its electrons. An acid, on the other hand, its job is to keep the electrons as close to it as possible. Lower energy, lower energy, lower energy. So, like I told you, first thing you do is figure out what job does each of these have. For reasons explained earlier, this is a base. Now we'll look at this. Oxygen is the central atom, more electronegative, and there's a plus formal charge. So with that, it has a pair of electrons. It could make a bond, but it's not going to. It's never going to. That's way too high energy. This is going to be an acid. It's much easier for it to lose that hydrogen than it is to make another bond. Plus, you're not going to have a base react with a base. There's no point. Okay. So the mechanism behind acid-base reactions is the base, these want to become low energy. So you'll take the electron pair on the base, it will attack the hydrogen. The electrons in that bond to hydrogen rock up to the central atom, which gives us these reactants. So from here we want to figure out, the same exact thing happens on this side, it's just the other way around. This attacks that, which rocks up to that. And we get back to this. That's why it's an equilibrium. This happens back and forth and back and forth. So equilibrium between acids and bases are going to favor the weaker side, the weaker acid or base, whatever is worse at its job. So you can either compare the two acids in this case, or the two bases. Although this would be the conjugate acid, that would be the conjugate base. So I want to look at bases. Look at these two bases. Which one of these is better at being a base? Well, if you look at this, nitrogen is less electronegative, oxygen is more electronegative, because that oxygen is going to hold on to those electrons a lot harder than this would. Therefore, this is a lot worse at its job. So this is the weaker base. Let's do the same thing with acids, although we'll figure out that if this is weaker, that has to be weaker. If this is stronger, that has to be stronger. Look at these two. They both have a plus formal charge, and their job as an acid to get rid of that. So which one of these holds onto the electrons in this bond with the hydrogen more? Well, oxygen holds onto it better, which means that it's more likely to lose the H plus ion than the nitrogen is. Therefore, that means this is going to be the weaker side, this is going to be the stronger, this is also going to be stronger. So because of this, equilibrium is going to favor this side. Even though we started with this, there will be more of these two components than those two components. Now that we know what acids and bases are, let's do some ranking problems. So our objective is to find the strongest acid. So which will create H plus ions the easiest, and which will hold on to its electrons the most. So looking at this, the central atom is going to be oxygen, nitrogen, carbon, and fluorine. So going across the periodic table, we know that fluorine is going to be the strongest acid, or the weakest base. It's going to hold on to the electrons the most. It's not going to use it. So horrible, horrible base when it's the conjugate base. So that's one. From there, which is the next most electronegative? Well, we know oxygen is pretty electronegative, plus like it doesn't even have carbon groups to stabilize it. So this will be 2. Then from there's the throw up between nitrogen and carbon. Well, periodic table, carbon's going to hold on a lot more strongly than nitrogen is, which leaves 4. It's just repeating this process over and over and over. It's really important to understand why this will react, whereas this won't. Let's apply what we learned. If this is the strongest acid, this is next strongest, this is the weakest acid. By extension, the stability is in opposite order. This is the most stable, this is the next most stable, this is the next most stable, this is the least stable. Unstable things will react. Stable things will not react. If we're looking for the weakest base, we're looking where there's the least amount of electron density, specifically on these oxygens. So if you look at this, there's a lot of electron density on this. So there's a partial negative there and a partial positive there. Let's go to the other. There's this. But if you look at this, this is actually a form of resonance, which means that there's another conformation of it possible, where you have the charge up here, and this is a stable double bond. So because of that, electron density goes back a little. So even though it has a partial negative, it's a lot tinier partial negative. That's a lot because it's sharing the electron density elsewhere. Because of this, there's less electron density on this oxygen than that oxygen, which means this is the weaker base, and this is the stronger base. Less electron density is more stable. We know the halogens are very electronegative. Also, I want to point out that even though I drew them in seemingly different ways, they're all bonded to the same carbon, which is bonded to that. So otherwise, they're identical, besides these halogens. The way you write them out does not change that. Back on topic. So we want to find out which is most stable. So more or less, which will have the least amount of electron density on these oxygens. Because of that, you look at the electronegativity of the halogens. So the least electronegative out of these 3 is bromine. So there's a partial negative there, partial positive there. That actually pulls back from this partial negative here. Chlorine is the next most electronegative because that it pulls a lot more. So this will be even smaller, this will be plus, and this will be even bigger. But out of all these, fluorine is the most electronegative. So there's this huge partial negative here, a huge partial positive here, and a very, very minuscule partial negative here. Because of that, it's withdrawing electron density to another part of the molecule, taking it away from here, making the molecule more stable. So because of this, this is the most stable, this is the next most stable, and then this is the least stable. Welcome to possibly one of the most confusing parts of this section, picking the strongest acid. So, I mean, normally everything we've done so far is off electronegativity. So you'd be like, okay, this is the most electronegative, then that's the next most electronegative, then that, and that. And you would be right. It does go in that order of this is the most electronegative, then this, then this, then this. But contrary to intuition, the strongest acids are actually in reverse order. Okay, so how does that make sense? Acids, the point of it is to make H+ ions, right? We're going to use the Bronsted-Lowry. Their job is to make these. Because of that, they hold onto the electrons really tightly. But the difference between these three, besides electronegativity, is atom size. And atom size will trump electronegativity for the halogens. So because that, like, fluorine is this big, iodine is this big, bromine is this big, chlorine is this big. So basically, because it's so large, the bond between iodine and hydrogen, which is like just a dot, is very, very weak. Because this orbital is so big, there's so many electrons concentrated in here, that the bond between these two is almost like degraded away completely. Because that, it's really, really easy for it to make this an H+ ion when something else comes and picks it up. And it's the same exact reason for the others. That's why bromine's better than chlorine, because it still has a good degree of bond degradation as compared to this. If that doesn't make sense, honestly, just memorize it, because it defies intuition. Because it's a lot closer to the atom, I look at it as, okay, it has a lot stronger pull, so it's less likely to make that hydrogen H+ ion. We're almost done now, I promise. So last thing I'm going to talk about is pKa versus pH and solubility stuff that comes as a result of that. So basically, every molecule is a pKa, and you can look back up at the definition of that. What I'm trying to help you guys understand is the difference between when these forms occur based on the pH. So the pKa of this molecule is 10. So compare everything relative to that. Remember, a lower pH is more acidic, a higher pH is more basic. This is a pH of 8, which is relatively more basic than this. This is an acid, and this is its conjugate base, because alcohols tend to be acids more often. So because there will be more of this form than this conjugate base form when in water. Let's go down to here. The pH is equal to the pKa. They're both 10. Because of that, there will be a 1-to-1 ratio between the two of these. And then if you go down to a pH of 12, that's relatively more basic than the pKa of this molecule. So because of that, there'll be more of the conjugate base instead. Why does water stick to you and gasoline doesn't? Why does oil and water not mix? The answer is because oil is nonpolar, whereas water is polar. By that I mean nonpolar, no charge. Polar, charge. Because of the charge, they attract to each other. The basis of solubility is like dissolves like. Nonpolar things will not be dissolved in a polar substance and vice versa. So because of this, water has a charge, whereas this will not have a charge. The electrons are shared equally. The electrons go here, and that makes partial positives and partial negatives. So to apply this, which layer, the nonpolar or the polar layer, would dissolve this compound? A nonpolar layer would actually dissolve this because this part right here is nonpolar. The nonpolar will latch onto that and it will dissolve in a nonpolar layer because of it. But the pKa of this is 5, the pH is 2, which means this is the acidic form, which this is like is. If you change the pH to 8, you will create the conjugate base of this, which will create a formal charge down here, which by extension means that it will leave the nonpolar layer and be dissolved in the polar layer. So to apply this, if you have two different compounds and you're trying to separate them into a nonpolar and a polar layer, you use the pKa stuff that we just learned to separate them. So this pKa is 5 and this pKa is 10. We want one to be the conjugate base and the other to be the acid, because if we have the conjugate base, that means it will be polar, the other will be nonpolar, and we can separate them. So honestly, if this is 5 and this is 10, pick a pH that's between the two. So let's pick a pH of 8. So compared to 10, 8 is relatively lower, so more acidic, so this will stay as is. But this pK is 5, which means that this would turn, there would be more of the conjugate base of this. So this compound would be separated into the polar layer. Thanks for watching, guys. Bye.